Mattel Incorporated is an American multinational corporation that manufactures toys. This is the stock prices from the years of 1998 to 2020. This is the equivalent graph of Cisco Systems, another American corporation that specializes in digital communication. Finally, this is the stock price of Morgan Stanley, an investment bank. Collectively, these stock prices form a resultant graph that is unsurprisingly complicated. Now the question is then, given some Q number of stocks, how can one optimize a portfolio? Even better, how can one optimize a portfolio by anticipating stock movement in a transparent manner without relying on opaque black box methodologies? We propose a solution through a multi-layer pipeline consisting of layers for interpretation, inference, and optimization. We process stock prices, extracting information at each stage to finally come up with an interpretable and accurate way of predicting and optimizing a portfolio. We start with the input data of stock prices. For every single time step, we extract the preceding M number of closing prices. In the interest of interpretability, we want to categorize these prices into distinct classes that signify the degree of deviation from some base value. These classes codify stock movements from the largest drop to the largest gain. For class formation, we employ kernel density estimation on our training data. This creates a continuous probability density function of a given feature. By identifying local minima as breakpoints, we can effectively cluster the data. To validate this approach, we applied it to the iris dataset, where we was able to cluster pre-labeled groups into clusters with a 96% accuracy. Benchmarking this against commonly used clustering algorithms, spectral clustering, dbScan, as well as k-means clusterings, we find that they were unable to do well with the same data. Utilizing KDE, we clustered each feature into distinct groups and assigned them fuzzy memberships based on their proximity to cluster centers. Clusters were then refined algorithmically to get clusters that look like this. Upon completing, we start to look at the price prediction problem. From our requirements, we need a predictive model that maintains some level of explainability. This requires two separate layers, one for forecasting future prices and one for interpreting the predictions made by the former. We start with the inference layer. Our inference layer is based off the transformer architecture, consisting of a number of encoder blocks as well as a multi-layer perceptron. The self-attention mechanism in the encoder weighs and embeds meaning for each input vector to capture more complex dependencies. Each model predicts a single time step into the future, and as a result, to find p time steps into the future, we need to create p different models. These models will then optimize with genetic algorithm to fine-tune hyperparameters. Additionally, Monte Carlo simulations identified the most important input features. The combination of the two yielded robust results. When testing with stocks from Morgan Stanley, Cisco Systems, and Mattel, we achieved an R2 of up to 99.7%. Despite occasional fluctuations in predictions, particularly with the Cisco stock, the model consistently captures and anticipates market trends effectively. We also benchmarked the model architecture using a similar process of genetic algorithm for hyperparameter tuning. Transformers generally delivered better performance, though was beaten in one instance for root mean square error by an LSTM. Having created a robust predictive model, we now can focus on interpretability. We base our idea of interpretation on Hebbian theory, which seeks to explain the phenomenon of synaptic plasticity. Within each neuron, there exist synapses which serve as the junctions where two neurons can communicate within the brain. The theory posits that the more frequently and persistently two neurons fire together, the stronger their synaptic connection becomes. To replicate this process, we implement a fuzzy rule base where each rule functions as a neuron. The more rule is fired, the stronger it is, and therefore the more important it is. These rules are structured on the Mandami rule base and are weighted by activation frequency and recentness. Through this system, we can visualize the most influential weights within the system. For example, in predicting Morgan Stanley stock price, the most significant influence was for the output 7th cluster. Inputs corresponding to that weight gives us a clearer understanding of the classes that might strongly impact future stock prices. Revisiting our pipeline, the inference and interpretation layers are modeled and mirrored across all stocks. The transformer layer predicts fuzzy membership for the outputs, which is subsequently relayed to the interpretation layer for Hebbian learning analysis. Additionally, the output layer also converts fuzzy membership into crisp outputs, setting the stage for our portfolio optimization process. The forecasted future prices are converted into several refined indicators, primarily MACD, RSI, and CCI. These indicators form the state for our reinforcement learning algorithms, among which are the Advantage Actor Critic A2C and Proximal Policy Optimization Algorithms PPO. A2C and PPO demonstrated the capability to surpass the performance of an average portfolio. A2C consistently outperformed with a return of 124% in our test dataset compared to 104% return of the average portfolio. PPO also exceeded the portfolio with a narrow margin of 107%. Traditional machine learning algorithms comparatively only peaked at 88.6% return. Now, having completed the development of our portfolio optimization algorithm, we've successfully executed the full scope of our intended pipeline, creating an anticipative portfolio optimization algorithm using an interpretable and evolving fuzzy transformer model.